Yeah. Even though we have the nice weather for a change outside, it's very nice to see you guys here. Today we have two exciting talks, but before we move on to the subject matter, I would like to welcome a short speech from our sponsor, Turku Science Park. So Mikke, please.
Okay, thanks. Hello everyone, welcome to Science Park, and this is the Spark community. Have you ever been here? Do you know this place? Maybe? There's a lot of startups being here and starting up their own businesses. So if you have friends and so on that are considering being an entrepreneur, have good ideas, welcome here. It's free of charge to be here for a certain time, and there's a lot of help you can get for your business ideas and so on. Did get this to work, so I just that doesn't work either. Yeah, okay. My name is Michael Lindholm. My work here in Turku business region is to coordinate AI activities, let's say like that. So it will be about a 2 years project, and welcome to contact me in any matter concerning AI. If you want help from universities, or if you want help from getting maybe pilot projects or anything, so you can contact me and I'll try to find you the help you need. We work in okay, now it works. It's you. In Business Turku, I would like you to join a Facebook group called Turku.ai, where we try to create a little bit buzz and talk about what's happening in the region. So feel free to tell about your own products or to talk about different AI-related matters there if you want to. It's meant to be this region, I mean the Western Finland. So let's keep it about that, but of course some other comments are welcome also. Let's change it. Then we have something we have 5 main areas we work with in Turku business region. It's clean, health, experience, maritime and tech, and the AI for the moment is the tech, but it covers all of those areas, doesn't it? So that's what we if you see clean or health, then we do certain things there. For health, for example, we have certain things going on, and in experience and other things. My last thing is to tell you about the 30th of May. We have a seminar about AI with example of existing AI solutions and products. This is aimed for, let's say, the normal entrepreneur, maybe not you're pros. So maybe for the companies that doesn't know so much about AI, and we have tried there to build a seminar about what AI is and where we can use it, and how a startup group has created AI for creating new businesses with coming from the universities. But okay, that's what I'm going to say. Please contact me if you want to and if you need help. So then we have the next talk. I will change your computer.
Okay, so the first speaker for today will be Teemu Roos from the University of Helsinki, and I think there's going to be something about a thing called elements of AI, which has created quite a buzz. Here.
Thank you. Okay, let's get the projector in shape. Okay, so thanks. Meanwhile, I'm a bit kind of dazzled this week because we started the Elements of AI, which is an online course on Monday, and It's been a bit of a whirlwind of interest and attention from all over the world. We have about 15,000 people doing the course already, and of course, when you release something and then you get that much users, then of course Murphy's law says that everything breaks down, and there's a bunch of exercises that are not correctly graded and something like that, but we've been able to kind of make everything quite all right in the end. So that's good. But I will not talk about so much of that. I was sort of going to maybe focus on that more, but then I was asked to talk more science, because I heard that you guys are sort of top scientists, and you only crave for the latest information and not the basics of AI. So I will not focus on the elements of AI course that much. Right, so we got the projector working, so it was not just a random projector. And that's interesting because I'm going to talk about random projections in the talk. Right, so I'm going to talk about something as simple as nearest neighbor search. Everybody knows, well, most people here, I'm sure, know what nearest neighbors means, finding the nearest points to one point. And that's a very commonly used building block for many types of AI algorithms and machine learning algorithms. So I'm going to talk about that. And we have some techniques that we have developed in my research group in University of Helsinki that I will tell you about. Okay, so here's the problem that we're going to address. We have a bunch of points, and for simplicity, we'll think of them as Euclidean, or as points in Euclidean space. So basically vectors. And of course, obviously, the illustrations are going to be 2D because I couldn't illustrate any higher dimensional things on a flat screen. But you can think of them as high-dimensional points in some d-dimensional space. Okay. And you can think of them being a lot of them. So this is sort of a big data kind of problem where you have some big number n of big number d dimensional vectors. And then we get, maybe let's say we have one more point, and we'll call that the query point. Okay? And that would be the blue dot in the middle. And our task is to find the points in our big bunch of points in our database that are nearest to our query. Okay, so hope at least this I'm explaining clear enough. And the naive solution that we would obviously use to solve the problem to start with as the first solution would be just to go through every one of the points in the database, calculate the distance between the query and that particular point in the database, and then choose the smallest distance, the point with the smallest distance. And that's fine. And that's a perfectly fine solution as long as you have a lot of time to do that. So the time complexity would be linear in both the dimension as well as the number of points. Now, perhaps we'd like to speed that up. Perhaps we are a streaming service. We have a lot of music in our database, and our users query for similar music somehow embedded as vectors of points, and the similar music then would be played to them through their device. And the users don't want to wait for a long time to get the next piece of music from their system, or they don't, maybe if we're doing web content recommendation, we don't want to wait, we don't want to let the user wait for a long time for them to get similar documents in a collection, if we can phrase the problem as nearest neighbors. So we want to speed it up, okay? It would be very, very hard to do that if we get the data and the query at the same time. But let's say we get the data first, okay? We have our music stored as some sort of vectors, that we can query, and we can do some processing on that database. And we have a lot of time to do that processing. So maybe we are able to do that, and then when the query comes, we have a way to isolate the small subset of our original full database. We'll call that subset S. And then we can only look at the points in that subset S. And if the subset S is much smaller than the whole database, then going through the points in the subset takes much less time than going through the data, the full data. So that's what we're going to do. We're going to build an index that, given the query, returns a small subset of the points, and then we're going to look for the nearest neighbors in that subset. That's the kind of the basic idea. And that, of course, requires that we have some processing time that we can spend to build the index, and then when the queries start coming, we can respond to them much faster than just going through the whole full data. Okay. So, and I really appreciate any questions at any point of time. So it's important that we get that kind of basic framework clear enough. So please interrupt me if there's anything unclear. All right. Let's put this pointer away. Right. So we build the index, and then there's a catch. If we have such an index that, given the query, returns a bunch of points, and then we only consider those points as the potential nearest neighbors, then there is the risk that this subset that we return, the subset S, might not contain the nearest neighbor. And especially if we are looking for not only one nearest neighbor, but maybe, let's say, 100 nearest neighbors, so we're doing K and N, with K equals 100, then it's kind of understandable that whenever we give such a subset, it could be that one of those 100 nearest neighbors is not included in the subset. But that's fine in many applications, and then we'll just call that approximate nearest neighbors. So we're kind of not solving the problem exactly, but somehow approximately with high probability or with some level of accuracy. Okay. And why would we want to do that? I already sort of mentioned a couple applications where such task is needed, nearest neighbor search, music recommendation or text recommendation, but there's a lot of other things too. So many clustering algorithms, for instance, take the data and then as a sort of a inner loop of the clustering algorithm, they require that you identify the nearest neighbors of a bunch of points. Visualization, especially many nonlinear visualization algorithms, such as ISOMAP or TSNE, which are called manifold learning. You may sort of maybe familiar with them. They also include, again, as a sort of an internal, sort of in the inner loop, which you go and repeat a number of time and time again. You're required to find the nearest neighbors of the points. So if you speed that stage up, you can speed these algorithms up, oftentimes quite a lot. Okay, so let's get back to the content recommendation idea. If you represent your text documents in some sort of a, probably not a bag of words representation, but some sort of let's say you do some sort of topic modeling or maybe some embeddings, you get these high dimensional vectors, and then similarity or relevance often can be represented as proximity in that space. So nearest neighbors gives you relevant documents. And we had this system built which we used to kind of demonstrate the algorithm. Well, this was actually the original algorithm for which the whole technique that we developed was invented, and that application later went to the semifinals in the Cambridge University Business Plan competition. So there's a plugin and there's a link. Maybe this will be given somewhere on the meetup page or what, and you can check it out. It's a Chrome browser plugin. Yeah.
Okay, so do you predefine all the possible subsets in beforehand?
Yes.
And how do you then select from the set of subsets?
So the index is going to be structured so that it kind of, given the, well, I will obviously explain this later, but given the query, it just traverses a tree, and when it reaches the leaf of the tree, there's it has a sort of a link, or it identifies the subset. So that stage is very fast. You can identify which subset it is for any given query extremely rapidly.
Yeah, and then you can create, for example, different sizes of subsets that how exact you want to be.
Exactly. Yes. So if you have a bigger subset, then of course it gets a bit slower, but then you increase the probability that you catch any number of the neighbors. Yeah. So there's a trade-off between the accuracy and the speed, and depending on the application, sometimes you don't really care if it's sort of so accurate, but you get really extremely rapid response, or you can sometimes have situations where you really want, let's say, 99.9% accuracy, and then you're willing to spend quite a bit of time. Okay, so let's look at how this method works. How do we construct the subsets of the points that serve the purpose of the index? I'll start with explaining what a random projection tree is, and this is not new. This is sort of this has been proposed in earlier literature, so we're just going to take this as the starting point for our approach. But let's look at the random projection tree first. And it's very intuitive of an idea. You have the points there in some space. In this case, it's 2D, but you can think again, if you can, of a high-dimensional space. And then you start slicing the space in half by hyperplanes. Okay? So let's do that. We have the points here, and now we're going to pick a direction at random, completely random. So I don't know which way it's going to be. Oops. Oh, this is going to, there we go. There's our direction, now it's this way. And it's splitting the data by first projecting the data along that axis, and then taking the median, because we want to get exactly half of the data on one side of the hyperplane, and exactly half on the other side of the hyperplane. And the hyperplane was defined by the projection vector, which is normal. And then there's another one. We chose another random direction. Now we only process the top half of the data and split them in half. And now next, after that, we're going to split the bottom half. So the second half of the original split. And there's our random direction. We're going to project the data. And then we just find the median. There it is, and that defines again a hyperplane. Okay, so it's just always recursively splitting the data exactly in half, because we look for the median. And that means that if you do 2 levels of splitting, it splits in 4. If you do 3 levels, it splits in 8, and it's always the power of 2 of subsets that you get. And we can represent this in the top right. Sorry?
Very quickly cluster now to.
So the subsets are now these areas.
Yeah, 4.
So there's 4 areas, yeah. And we have now, and those are the smaller subsets that I talked about. That each of those areas, that in this case contain 3 data points, each of those is a subset S that we could return. And then when we get the query, anyone guess what we're going to do? Which subset? If I get a query, it's not going to show in the video, I'm sorry, but if I get the query here, which subset I'm going to get? It is not a trick question, it's kind of, is this one, yeah? Right, and that's my subset. So that's the way I pick the subset. So let's put the query there. And I retrieve the subset that has points. If you're very careful, if you have binoculars, you could even see the labels. It's A, D, and H. Those are the points.
This is very natural because my brain working this and responses very quickly equal the situation.
Right.
Is you choose the patterns, and it's so interesting this because if you put a handle And this, if it not exactly, is a good response.
Right. So I guess our brain is very fast at doing this in a way, and I guess that's got something to do with the fact that we kind of associate very easy things into roughly some area of our field of vision. So I guess that could be something to do with how we actually do it as well, if I understood what you meant. Right, so now what problem do we have here? Did we do well? Yeah?
Well, for example, you are a bit on the left of 8.
If yeah, well that would be a problem. I wouldn't find age. There's an even more obvious problem. I don't even have to say if. Yeah?
Because its neighbor is not actually in the subset.
The nearest neighbor is even in this example not in the same subset. Right? The algorithm would claim that the point D, which is labeled as a light circle with red, is the nearest neighbor, but it's not. Because there's another one just below one of the hyperplanes, point I, that is. And that is the actual nearest neighbor. So there's an error. We didn't find the nearest neighbor. And now the people in the back are already starting to go to the pizza and the beer. But we're going to make it better. Don't lose hope yet. We're going to fix this problem. And that's basically the work that we did. That's the thing that I'm going to talk about really. This was just the background. Okay, but you can see that this strategy will be good in the sense that it speeds things up. If I make the depth of the tree 10, that means on each side of each hyperplane I keep repeating this recursive splitting 10 times, then I split the data in 1024 subsets. And each one of them is the same size, plus or minus 1, or plus 1 or not, actually. And that means I get 1,000-fold speed up in the stage where I compute the distances. Traversing the tree doesn't, we'll get to this speed actually right on this slide. So how long does it take me to construct this index? Well, I have to, every time I split, I process every single data point. I process it in one side of the hyperplane or the other, but nevertheless I have to go through all the data points on every level of the tree. Each data point is projected exactly once. And there are, if I say that I need the subsets to be size n naught, so my full data is n, and then n naught is the size of the data that I'm willing to allow in the subsets in the end. So in the previous one, n was 12, and n naught was 3, so there's 4. There's a ratio of 4 in terms of the size of the partition, or the cells in the partition, and the full data set, and the log of that tells me how many times I have to split. Okay? So that's the depth of the tree, log of that ratio of data points. And since I process every data point exactly once, then and processing a single data point, projecting a single data point, it's a d-dimensional data point, and a projection is a linear operation. So that's d operations per data point. So it's n times d per level, and that's the total time complexity. Okay. So let's look at the time complexity of the query stage, which is more important to us. We can spend much more time on building the index, but we'd like it to be very fast at the query stage. Okay, the query stage, first we need to route the query in the tree to the corresponding leaf. Okay, and again, it's the same process, it's a projection that we need to do to decide whether you're on the right or the left of each hyperplane. So that's d operations per level in the tree. So it's d times then the depth of the tree, the log term. So d times the log term, and then we know in which leaf we are. And then we have to update the computer. That's all right.
If you have a subject in your case that have a structure that you have a easy index
Mm-hmm.
and you put in this structure is it's 40 times more quickly than the normal algorithms to facial to facial recognition, because you have the index of the dimensional structure. You have this and this and
Mm-hmm.
it's a good idea.
Okay, well, that sounds good to me. It's a good idea. Well, let's get back to that in a bit, okay? Right, so how long does it take for me to do the query? We decided that it's the depth of the tree times the dimension, so that's d times the log term. And then once I reach the leaf, I need to do n naught distance evaluation, so that's d times n naught. And that's the time complexity. And we can see that that's obviously much faster than, of course, computing all the distances in the full database, and that's what we wanted. The thing is, we're going to need this asymptotic time complexity to make a certain trick to get rid of the errors, and that's why I'm boring you guys with this. Okay. The issue, of course, is that the deeper I make the tree, then the smaller the leaves, and the more chances there are that the actual nearest neighbor is on the wrong side of one of the hyperplanes. So on the far side, looking from the query point. Okay. This one I'll skip. Locally sensitive hashing is kind of a common way to solve the same problem, but there's a relation, but we don't have time to get into that. Okay. Okay. So we agree that this is a sort of a reasonable approach, but it might fail to find the nearest neighbors. This is sort of just repeating what we learned. Okay. So here's a very sort of simple sounding solution, and that's kind of, I have to say, it's a simple method, but I'm kind of very happy about it being simple. I think that's a good thing. So we tried t times. Okay. So you try and you look for the nearest neighbors, you get a set of points, and you try again. You get a set of different set of points. So, and there's randomness in the algorithm. So, since that's a slightly different set of points, and then you just look at the nearest point, like which ones of these points are let's say the 10 nearest, in this set or that set. And again, there's a bigger chance that one of those two sets is going to include the actual nearest neighbor. And then you repeat once more, and again, the chances that you found the true nearest neighbor or the true nearest neighbors increases. So the more times I try, the better chance I have to succeed. But of course, it takes t times more time. Yeah, just to repeat it t times. How much more? Well, it's obvious. You just multiply with t. Building the index, well, t times more time. Doing the queries, t times more time. But now comes the key idea, and I put it in red and big letters so that you would focus hard right now. So here's the key idea of the talk. I even named it KIT, like the car of Knight Rider. If we decide that every time we double the number of trees, we halve the number of points in the leaves. How do we halve the number of points in the leaves? Anybody? How do I halve the number of points in the leaves? What do I have to change in the tree so that I make sure that in the leaf nodes in the cell of the partition, there's half the number of points than there used to be?
So just do another
one more level in the tree. Good. Right? I do one more split, and because I split at the median, I split the number of points that remain in the cell of the partition. I split that in half, and because that's the dominant term, n naught goes to 1/2 every time I increase one level. That is the dominant term in the time complexity in the query stage. I then make every one of those trees twice as fast. They take half the time that they used. Okay? And now you see the point here. I double the number of trees, but each one of the trees is twice as fast to process. So the time complexity really doesn't change. Okay?
And in parallel?
And I can do them in parallel, and then of course I'll be happy, but there's going to be news for you even if I don't do it in parallel. Yeah, let's get back to that. So this is just to repeat. If we accept the fact that I claim that the second part in the query time complexity is the dominant part, then the time complexity really doesn't change when I double the number of trees and make them one level deeper. Okay, so here's an illustration just to make sure we were on the same page. We have some 400 data points, and we'll just represent them. Each 100 data points is now one blue dot. I didn't want to draw the full screen full of dots, so I just used this shorthand notation. So here's one tree. There's one level in the tree, and I split the data in half. Okay. And the time complexity to do the query is not changed if I double the number of the number of trees by adding one level more. Because in the query stage, okay, now I'm going to step out the screen again, but you guys will see me. So if in the query stage, I will process these points, and then in the other tree, I will have to process the other set of points. But each of them only has 200 points instead of 400. So it's 400 points to which I need to calculate the distances altogether, and the time complexity remains more or less the same. And here's another nice illustration in color and all. This is just a bunch of 2D points for illustration. The power of the method really doesn't come about in 2D. It sort of works much better in high D. But just for the sake of illustration, the red dot in each panel, well, the data are the same in each panel. The red dot, the query, is the same in each panel, but the hyperplanes, which are just the random projections, or which are defined by the random projections, they are always the same. And you can see that the cell in which the query point lies, it looks very different in each of the panels. Of course, the query is still like roughly in the same area in the space because the query point pinpoints us to the right cell, but it's a different shape. And if I put those on top of each other, it looks like that. Those are now the sets combined. And I'm going to search for the nearest neighbor in that set, in the union of those cells. Okay? Ideally, by the way, and this is an interesting thing we're trying to kind of understand theoretically, ideally that set should have the shape of a sphere, or in 2D a circle. Why? Well, because the sphere is the smallest volume that contains the nearest neighbors. Right? There's no point in looking at something that is further away, because the nearest neighbors always are inside a particular radius sphere. So I would like that set to be a sphere, exactly centered at the query. But that I can't do exactly, because I don't have the capacity to build those subsets for every possible query that they could be. I don't know the queries in advance. That's the hardness of this game. But then, if I look at the overlap of these, on the previous slide, of these kind of funny, I think they're called polytopes, so areas defined by a set of hyperplanes. These polytopes, the overlapping area, not the union, but the overlap in the sense that the more times I get them stacked on top of each other, the more polytopes that cover an area, the better, then that becomes more or less a sphere. But that's an empirical observation which we can't really prove.
But infinite time to put this You have a real history.
We'd like to prove that. Unfortunately, that seems to be not true. And that probably explains why we couldn't prove it. Usually very hard to prove things that are not true. But we tried for a long time. So not for lack of trying.
Oh, yes.
Okay. But it seems it goes roughly to the shape of it becomes more spherish. Okay, that's to use a technical term. Okay, so I gave you the idea. The time complexity doesn't really increase. The dominant part in the time complexity doesn't increase if I double the number of trees, make them one level deeper. And I can repeat that again. I can do them. I can make it 4 times more, and then increase the trees level by 2. Or I can make 1,000 trees, and then just make them 10 levels deeper. And the time complexity, in principle, it shouldn't change. Well, there's the non-dominant part that eventually will kick in if you have a huge number of trees. But for a moderate number of trees, what I'm saying is true. So it doesn't significantly affect the query times. Okay, that's what I've argued so far. Okay, but does it help? Right? Doesn't affect the query time. Well, so what? Yeah. Why would you be interested about that? Well, there's more. Now it's time to focus again. Big letters, colorful letters, key observation of the talk. So that's good. Okay. All right. And so focus. Now it's coming. If you do more trees that are deeper, it doesn't get slower. That's good. But it does get more accurate. It does get more accurate, and that's the big thing. Okay? So it's not getting slower, it's getting more accurate. In that sense, there's no trade-off. It's a free lunch, or free dinner, I guess, as here. So here's a demonstration on actual data. This is Wikipedia data, 500,000 data points. They are now represented in a 1,000-dimensional representation. There's a topic model, LDA, that we run first. The curves, well, first of all, the plot, if you go to the right, you're spending more time. If you go towards the right, you're spending more time. That we can still do by saying that let's do less levels in the tree, but keep the number of trees the same. You can make it slower, and it gets more accurate. So that there is a trade-off of that kind. So easy to make it more accurate if you make it slower. Okay, well, I'll get to the important point in a second. Then the higher you are, the more accurate it is. Okay, that's the fraction of the 50 nearest neighbors in this case that you get. At the top of the curve, you get every time all the 50 nearest neighbors, every time you do a query. At the bottom of the graph, you get 1 of the 5. Doesn't go all the way to 0. And then between, you get more or less of the neighbors. And the different curves here, those correspond to different number of trees. When we increase the number of trees but make them deeper, we're going up in the graph. We're jumping from one curve to the next. And as I said, the time complexity doesn't really change. So let me repeat that. If I double the number of trees and I increase their depth by 1, the time complexity doesn't really change, and that is shown by me jumping one curve up. Let's say from the blue curve to the green, or from the green curve to the orange, or from the orange curve to the purple. I'm jumping up, not to the right. So it's more accuracy, but not slower. And that's the demonstration of the key observation. You double the number of trees, you increase the depth by 1, gets more accurate, but doesn't get that much slower. Or you can tweak the other parameters so that it actually doesn't get slower at all. All right, so that's the, I mean, if now we lose power, I'll be happy because I've shared this. This was the main thing that I wanted to share. Yeah.
Are there any drawbacks of using more trees?
Eventually, so when I said that you double the number of trees and you increase the depth by 1, the dominant term in the time complexity doesn't change. But you can actually see, I think that's, if I read the term, if I read it correctly, you would jump only ever so slightly to the right. So if I have a huge number of trees, then eventually there's the non-dominant part that starts to dominate the time complexity. So that at some point this breaks down. But it doesn't break down very easily. So you can have thousands of trees, and still it holds that the time complexity doesn't decrease if you always just keep remember to make the trees deeper. There's a space requirement. If you have more trees, then you need more space, and especially because those trees then have more labels in them, so you need to store more random projections. So the space complexity does increase. That is something that is hard to do something about. Actually, we can make the projections sparse, so in that case, it turns out that the space complexity is really not that big an issue. But it could eventually be if you have, especially if you don't do sparse projections. There was a question there.
You're doing the projections at random, right?
Yeah, completely at random.
Is there any smarter way to do that? Like you're using multiple trees before you want to do it?
Yeah.
Complementary or something?
Yeah. That's a good question. We've had that kind of an itch at the back of our head that really, could it be best to do random? How can that actually be the best thing to do? But then it's very, very hard. Like we could think of very smart things. I mean, we could think of BCA kind of things where you split data along the dominant variance direction, and that would sort of be such a nice idea. But then what we lose is the benefit from having multiple trees like that. So if it's completely deterministic, there's no point at all to do more than one tree because they're all the same. It doesn't help at all. If you don't find the neighbor in one tree, then you won't find it the next tree either because they're the same. So it's very, very hard to find the balance between randomness and then optimizing the projections.
Do you have any metric for like successful queries? So you could just do multiple divisions into T3s and then pick the best division that has this kind of query metric.
Right, yeah, I mean, that of course, yeah, we can then try. The nice thing about this one is that it's really, like in machine learning, it's really hard to try a number of things and then choose the best because we don't really know the outcomes in advance. It's only later when we know the outcomes. We can't sort of, let's choose the method that predicts best whatever is going to happen because we can't know what's going to happen. But in this case, it's not like that. We can take the data, and we can try a number of things. We can try a number of parameters, or we can try different ways to choose the projections, and in the end, we can pick the one that works the best. So that we can do. But it doesn't really change that much when I try one bunch of random projections and compare it to the next. It's kind of converging in some sense. There were a couple of hands.
Yeah, I was wondering about these tree building algorithms that have you considered how to add daily deltas if you get new data to your universe?
Yeah, it's sort of nice how you guys are asking exactly the questions and exactly in the order in which we came up with the same sort of problems. That's an open problem. We have thought about that. We just haven't implemented any of the ideas that we had about that. It should be easy, especially if the data keep coming from the same source. But yeah, like that's a kind of an ideal world where the data keeps accumulating and it's always from the same source. I mean, in real life, of course, the data always keeps changing. There's concept drift and all that. And that would make it interesting, and at some point we'd have to start balancing the tree because there's more data coming in one part of the tree that gets extremely deep, and we kind of lose the power of the logarithmic depth in the binary tree. And at some point you'd have to balance, but I think it's kind of a nice problem where we've come up with some ideas. Now we kind of just need a couple master's students to experiment with them and solve that.
I'm still missing my master's thesis.
Okay, well, so let's talk about that. Great. Did you have a question?
No, I only comment. This is so interesting in mathematics and logic because Komagorabi and Shaitin explained us about the handle and the information inside of handle.
Right.
And it's so interesting this because you have that omega of citing, the idea of omega
Right.
of
Yeah.
citing inside of this, and the citing tells
Okay.
that you see this, you see the information, and
Okay.
this is so interesting. And another comment is about your law is about the frequency of fractal frequency, and you see the fractal frequency in this, and it's possible understand the exact point to stop.
Yeah, that's a good point. I really can't see like the connection to Chaitin's omega, but it's an interesting point. The theoretical analysis of these kind of algorithms, if you look into the probability of failure, you're eventually going to run into something called intrinsic dimension. And that has to do with the fact that even though we might have a 1,000-dimensional data point, it tends to be so that the data lie on a low-dimensional manifold that is usually curved in that space. And the dimension of that manifold, not the dimension in which you represent your data, which could be like 1,000 here, but the lower dimensional structure, manifold structure, that is a key term in the theory of what is the chance of failure. So actually the fractal dimension or the doubling dimension or intrinsic dimension are all kind of connected terms. That plays a significant role in the theory of all this, which I haven't had the chance to go into at all. Okay, so here's another, let's move on because we're to a bit short of time. Here's another experiment where we now take our algorithm with whatever parameters we found out to be optimal here, again, just trying out a bunch of different parameters, and compare it against every other algorithm basically that we found for this problem. This one that we have hard time beating, most of them we beat hands down, but there's a graph-based algorithm, K-graph by Dong et al., already 2011, which is extremely hard to beat in this data and others too. But there seems to be a tendency that so the red curve is ours and time goes up, so that you want to go kind of, you want to be low. And accuracy is towards the right. So we'd like to be in the bottom right corner of this graph. Accurate and fast. So in the high accuracy range, it seems that we get the state of the art in the approximate nearest neighbor problem in basically any data that we tried it on. We've got all the benchmark and all the implementations on GitHub, so you can actually try it if you like. Okay. Yeah, these I'll skip. There's a couple kind of further ideas, which I'll just summarize kind of and mention in passing. We already discussed a few of them. Well, this is almost embarrassingly parallelizable, which is actually the technical term, if you know. So there's not much that you need to let the trees to sort of talk to each other, but there is some, and we're actually currently working on doing that, so that you get almost linear time speed up in terms of the number of servers that you can distribute the data over. If you do sparse projections, it's remarkably insensitive to the sparsity of the vectors. So you can really do the number of non-zeros in the vectors. So if the length of the vector is d, then square root of the non-zeros is sufficient. It's really sort of in the limit that it's all zeros, almost. Or the density of zeros goes to 0. And there's really no loss of precision due to that. It's kind of remarkable. And then with that, if you do the sparse projections, then it's very compact, the representation of the structure. There's interesting theory that we're working on, and we have some results. I didn't really talk about that. It's related to it kind of boils down to very, very simple and elegant geometrical problems, which we've been looking into, starting from some work by Dasgupta. Now we're working with Dasgupta's team and simplifying the results and then extending them to multiple trees. So the previous results, they only apply to a single tree, and now we just need to extend those to multiple trees and deal with some additional features of the algorithm. But it's very, very interesting and nice theory that's coming out of that. I won't go into that. So yeah, we can prove, it's like this is the proof. It's that long that says that more trees is better, and that sort of matches with the empirical observations as well. So that's nice. Yeah, parameter tuning. This was the question was asked. That's the master's thesis project. Doing incremental index, so if you add more points or change of the points, take some of the points out, and you wouldn't have to build the index from scratch. It should work. We can parallelize that. That's what we're working on. The projections are nice because they're basically dot products or matrix vector or matrix product, and then you can just put them in a GPU and you get pretty nice speedups. And then this was the other question: is random really the best we can do? That's a tough one. We don't have that good ideas on that either, but it'd be fun if you do. And now we're there. I think I sort of made it just in time. Just to summarize, it's a simple algorithm. I'm a simple man, so I like that. You can accelerate it nicely if you have some dedicated hardware. Especially in terms of the dimension, it scales really well. Basically, you could say that if the dimension is higher than 1,000, or especially if it goes to something like 10,000, then it beats everything else. For lower dimensionality, then you might have other methods that are better. Even brute force approaches, which the guys at Google were very keen on sort of arguing that if you have sort of big enough a computer, then you can still do brute force. Fair enough. Maybe I don't have that scale computers. And yeah, good accuracy levels. And it's all open source. Everything is freely available. You can find the papers on the theory on my homepage. And then final, I guess I already mentioned, I don't know what the number is, probably more than 15,000 students now taking the course, so you're also welcome to check it out, but it's probably nothing kind of technically new to you guys, but you could maybe recommend it to your spouses or moms and dads and whatnot, just to make this country and the world more AI literate. So then we can talk about these kind of things also at home or in the bar. Wouldn't that be great? Okay, thanks. So I guess maybe by the fact that we're 3 minutes over time, we can talk more offline, and we'll let the other speaker on the stage.
I suggest we take like a 5-minute break. Bathroom here itself.
Sounds good.
Silloin olisin jonkunnäköinen,
Feel free to grab a drink or hints or boats with you. Okay, I guess we can start. So our next speaker is Tuomas Piippo from City of Turku, and he's going to talk about the city data lake and smart and wise city plans. Please go ahead.
Okay, thank you. Yeah, I'm Tuomas Piippo. I work as a development manager at City of Turku in our strategy and development unit. And I think in this event's description you were kind of promised 2 experts, but I can say that I'm quite far from an AI expert, and that's why I really like the naive solution that you proposed in the beginning. I've studied computer science here at University of Turku, and I've been a project manager in some data science or data analytics or machine learning projects, so I think I kind of know the basics, but I'm quite far from being an expert on this field. Lately I've been working on planning this new Smart and Wise Turku program that the city is now starting. The program is not directly linked to data science or analytics or artificial intelligence, but one important theme here is better utilization of data and having the data owned by the city utilized better than it is currently, and I think there is very close connection to data science and AI. So about the program, the city board has decided to start planning the program in 2017, but actually this week's Monday they made the decision to start the program according to these plans, so it's a good time to be discussing these things. As you can see, it's about creating a smart city as well as a wise city. I think smart city is a kind of problematic term since the definitions vary a lot, and I think a lot of development initiatives can be labeled as smart city projects, but usually I think it's somehow about responding to these kinds of problems that cities are facing by better utilizing data and finding innovative use for technology. And the wise city part is a bit more unique to Turku. It's about including all the citizens in planning these smart city solutions, as well as making sure that all different groups of people benefit from them. So it's about doing smart things and maybe doing also right things. There are these 6 areas of emphasis in the program. Carbon neutrality has been ongoing for a while. City of Turku aims to be carbon neutral by, I think it was 2040. And currently we are actually kind of ahead that schedule, so we are doing better than planned, and that thing is going forward. Customerships and service management, that's a large subject that could be its own speech in a different event. It's about having a holistic view on our customers, meaning the citizens usually. It's about not viewing the citizens only as patients or students from some specific services point of view, but having a holistic view on them and then designing the services for different customer segments. And that's a large change on how the city has currently been planning its services. Then there's urban design. I would maybe translate it as urban planning, but it's about planning the urban environment. Some of the concrete actions there are better utilization of 3D models, so that the planning of areas and buildings would be as seamless as possible using the same 3D models. In safety and security, I think one of the most important things is creating a common information and set of information and common view for different authorities, so that the city organization and police and fire department would be operating using the same data. In traffic and mobility, City of Turku is already part of European Union's program. It's Civitas Eccentric, and they are advancing smart traffic solutions and mobility as a service and that kind of things. And the City of Turku received the city bikes in this month, and that is on behalf of that project. And the last one is prevention of social exclusion. I think that is an area where better utilizing data can help us, since we have data from schools and health services, unemployment services, and maybe better utilization of that data might help us prevent social exclusion. So these are kind of project portfolios for these different areas, and then we have these cross-cutting concerns. Platform economy, I think it's almost as trendy topic as AI is currently, but the idea is that the city is not doing everything itself, but it's creating a platform where different companies and citizens can also create things that benefit these areas. And I have been most involved in the area of data utilization and data platform. And I thought that instead of just having a look at what we are currently planning, it might be more interesting to understand how the plans evolved. I'll go through these three phases separately, but the overall thing was that we started from more of a technical integration platform. Then we discussed kind of business platform and creation of an ecosystem for utilization of data, and the current plan is to create this city function to advance these things. And please ask if you have questions at some point. So the basis was that if you go to a smart city event, they have some solutions for very specific problems. For example, in Barcelona, if you visit the vendors, they have some smart trash cans that are able to tell you if they are full and things like that. But they solve a very specific need, and the solutions are not designed to work together in any way. So we thought that we will need to create some sort of integration platform or utilize some sort of platform to get these solutions to talk to each other.
Oh,
yeah.
Return, please.
Yeah.
The prevention of the social exclusion. This is a big problem, but I am Brazilian, and in Turku have many people of different parts of the world, and it's a clear problem of the social network. It's you have the people here living little networks, and
so you are not already part of a network.
The easy solution is mix in Brazil is mix more, and this is difficult to resolve this problem. But if you have plotted this data in Brazil, you have a problem with the persons with schizophrenia, that we put only 2 persons in the network, more 2 persons, and this is fantastic. Change the problem, and it's easy to modulate this problem.
Maybe since we are discussing data and AI, I kind of wanted to highlight that we are utilizing data there, but the person responsible for this part of the program, I think she is a social scientist or a social worker or something. She has different background than data science. So even though I wanted to highlight that we are utilizing data better, there are of course other competencies and lots of other things are done as well. But that's a good point. That
so important to the future of this city. This point, all points is important, but this point is crucial.
Yeah, this is actually something that when we had the new mayor, I think it was late last year, this is one of the first things that she wanted to include. So I think that is quite high on her agenda at the moment. Okay, so we briefly consider just having a technical integration platform for all these solutions, but well, first of all, it's usually probably more relevant to integrate these solutions to existing city systems, since we have something like 200 to 300 information systems at the city, and they contain a lot of information from different fields of urban life, so it should be priority to utilize that data as well, and maybe we should not limit ourselves to just producing and consuming data as a city organization, but we should maybe include other parties as well. And it might not be enough to just technically publish the data to make it available through an interface. I think we will need to somehow actively support the utilization of that data. And the kind of second phase of this planning was this model of circular economy of data. And we kind of loaned some terminology from circular economy of physical goods and raw materials, where it's important to create value with a product, a physical product, throughout its life cycle. And we try to do the same with data here. If we think about this city area, the physical world, we can of course think that nowadays almost everything creates data. People are moving here and making purchases and using services, and sensors are creating more and more data. And I think the first thing is that we should try to capture as much as possible of this data. And the word digital twin is often used just to describe these 3D models that you have of the physical environment, but we are using it as a bit broader term that includes this data that is created by these local events. And of course data is immaterial and global by its nature, so I think it's also a good idea to kind of include the data that is relevant to city of Turku and this area from global data sets as well. And then the other part is that if we have a lot of data regarding this area, we as both the city organization and citizens and companies, we should be very efficient in utilizing it, in creating new business models, creating new services, improving organizations' operational efficiency, which can be usually done with better data. And therefore we can hope that a lot of data utilized effectively is improving the well-being and competitiveness here on this area. And with little data and mediocre data utilization, even the trees are not doing very well. This is the naive picture of this presentation. Yeah, so we identified this circular economy of data as a good target state, but we would need to think of how to get there. And considering platforms, it's usually important that if we want to form an ecosystem of different actors on a platform, we need to have kind of a critical mass of content and participant on a platform. And for reaching that critical mass, it's maybe important to start by publishing data that is owned by the citizens. We have most control over that. And that arrived at the creating a Turku data office, a city function that manages these data assets that the city has and tries to advance their utilization by citizens and by businesses and universities. We identified, this was done with Solita, I think, we identified these 3 paths towards that kind of ecosystem where we are good at utilizing data as a ecosystem. I think the lower one is the most traditional in the way that usually open data and open APIs, it's published with the idea that someone might innovate something on top of that data. It's not usually, we don't start from any businesses or customers' needs and what kind of data they are needing to solve a specific issue, but usually data is published and with more and more data we can expect that new innovative uses for it arrive. And then there's this opposite one where we are starting with discussing with companies. We try to identify some issues that they have in their operations and problems they are facing, and try to identify the root causes and the related data-related issues, and then try to match that with data that city is able to provide them with. And this middle one is maybe the most straightforward in the way that there we are cooperating with research organizations, universities. There's this Turku Complex Systems Institute from the mathematics department that we have been cooperating with, for example, and there we are kind of solving these systemic problems and issues with utilizing data. The last few slides contain kind of a process view on what we are doing in practice. We identified these things as kind of core processes, so we are somehow identifying or creating demand for the data that the city owns. Then we are actually producing the data, producing it, and then at the third part we are delivering it to its possible users. Here I think this is the most important part in a way that this slightly differs from the traditional way of publishing open data. So we work with customers, meaning companies or organizations, and try to identify their business problems and what kind of analytics problems they mean. And also at the same time we kind of try to find use for catalog data that we currently are able to offer them. And using that information we are able to identify demand for data, and then we can try to kind of match the data that is currently in cities systems. Then in this part we have identified some activities around the data lake that we will need to do to better utilize the data. Since there is really a lot of information systems, a lot of data, we will need to be able to prioritize and select what to publish and what to utilize. And then there is a need for some sort of digital channel. We are working with these local companies face to face and meeting them, but it's necessary to have some kind of channel to publish this data as well. So we started from integrating these smart city solutions as a technical platform. Then we discussed this business platform that contains both the technical solution and some processes, and then we came up with new function for the city of Turku that is built on top of this technical and business platform. Thank you. So, yeah.
Do you have any ideas now on time schedules on different parts of the project?
I think we can start implementing these things after the vacations. We have now the decision from City Council on this entire Smart City program, but the mayor will make a separate decision on creation of this Turku data office. So I would assume that when the holiday season is over, then it's possible to start.
I have a question about what is the situation now? What kind of data does Turku provide sort of via APIs, and is any of data free use?
Yeah, there are data sets in Turku. It's Lounais-Tieto, I think is the organization that is publishing open data, and it's, of course, I'm not part of that organization, so I will need to consider my words very carefully. But I think if you have a look at what is now published, there are, for example, some Google rated. So there are this location where you can go and run, and there are there is data that it's not very easy to combine. It's very different fields of life. And I think here we will try to publish data around specific areas. So there would be a lot of data regarding this area and this area. And it's a bit different approach from what has currently been done. And the current open data initiative has been a joint initiative of the 6 largest cities. So this is done a bit more locally, and the emphasis is on identifying the data that the city owns and finding use for it. So bit different approach, but I think this is kind of building on top of what has already been done.
About legal issues now that GDPR is coming, does the city of Turku own all this data? Does it have personal data and can citizens access it?
Yeah, I think we will definitely start with data that is not related to personal data. I think our technical services contain a lot of data about, for example, the built environment, and it's probably better to start from that. And yeah, that's true that when we try to utilize data that has been created or is related to citizens, then we need a kind of different approach at that time. But we will start from other kind of data.
So I guess if one thinks of how to best build or how to best design a platform that supports some like really nice applications, then I would imagine it's extremely hard to think like for a group of people in the project to gather together and then be able to conceive in advance what would be the needs from the platform to whoever is going to build something on top of them. So I suppose you must have in mind some use cases or some pilots projects or maybe some examples from other cities, from other countries maybe.
Yeah.
So do you have some kind of like use cases that you could think that, okay, we want to support this kind of activities, please, and that and that?
Yeah, I think we will have multiple approaches. One of those is to actually meet companies and identify their business processes. Yes. And identify the problems there. And there it's easier to notice that, okay, we are doing this thing now this way and it's causing a bottleneck in our process. And with this data we could work otherwise. Right. So that's one part. And of course, identifying these good ideas from other cities is one way, and then hackathons and things like that for finding.
You're saying that you're already kind of progressing with the project, and after the holidays you'd be sort of implementing some project.
Yeah, we have had some workshops with companies, so that is.
You had or you will?
We have had, and the next one will be in June, and that has been actually done with the Bastu network from the University of Turku. So they have an existing network of companies. And
can you give some examples that have been discussed in those meetings, or is that kind of not?
It's not about that, but we are not that far actually yet. Okay. So I hope that on the next workshop we can actually identify some data sets. It has taken. We had one meeting just to know each other, and we have had one actual workshop at this time. But I hope that the next one will have some concrete data sets that they are requiring. Okay. There is not my email address, but it's tuomas.piippo@turku.fi. So please contact me if you have some more questions or some use cases or ideas for utilizing data or AI within this project.
Thank you, Tuomas and Teemu, once again. So that's it for today. I think we can stay for 20 minutes or something. So feel free to chat with each other and grab a drink. The next meetup is not entirely decided, but we'll probably have one in June and probably at the University of Turku. But there will be more on that later on. In July, we'll probably not have a meetup. We'll go on vacation like the rest of the country and get back fresh in the August. But more on that later, so please follow us on Facebook and Turku.ai about the next meetup. Thanks for coming.
And please, eat more pizza.
Yeah.